Okay, so now I will start with full wave rectifier. So in half wave rectifier, we saw that if the input voltage is like this, the output voltage will look like, when the input was positive, we get the same voltage, the output. When the input voltage was negative, the output voltage was 0. Again, when the input voltage is positive, it was like this. So it was kind of a pulsating voltage. So with full wave rectifier, we'll again get pulsating, but here the output voltage will look like this, output of full wave rectifier. So now let's see how the circuit of the full wave rectifier looks like. See, the full wave rectifier basically have two types of full wave rectifier. One is center tapped full wave rectifier, and another is diode bridge full wave rectifier. So in this video, we'll basically discuss about the diode bridge full wave rectifier. Okay. So how this circuit looks like, circuit of the full wave rectifier. So we have diodes connected in this manner. So here we can connect the load. Suppose we are connecting our load here. Suppose there is a voltage across the load. Define one polarity here, positive, negative. Fine. And the input is AC. It is Vm sin omega t. This is Vm minus Vm okay. Now let's see how the circuit behaves when the input is positive, that is for the positive cycle. For positive cycle, let's check the behavior. We are considering the positive cycle here. So when positive cycle, the polarity will be like this. Now when the input is positive, which diodes will be conducting and which won't be conducting, which diode will allow the flow of current, which diode won't allow the flow of current. So let's suppose there was diode 1, diode 2, diode 3, diode 4. Now I want to check which all diodes will conduct. So I have, as discussed in previous lecture, to check which diodes are conducting, let's first consider that none of the diodes are conducting here. Okay, all the diodes are in open circuit condition. Suppose this is the anode of diode 1, cathode of diode 2, anode of cathode of diode 1 here. This is the cathode of diode 2. This is the anode of diode 3, cathode of diode 3, anode of diode 4, the cathode terminal of diode 4. Okay. Now check. Now we'll check individually. Now let's suppose we'll check for the diode one. Basically, we'll check whether the anode voltage is higher than the cathode voltage or the cathode voltage higher than the anode voltage. If the anode voltage, if anode voltage is higher than cathode voltage, then diode 1 will conduct. Okay, or it will be in forward biased. Let's see. So now what will be VA1? What is the voltage? So VA1 is basically VA1 with respect to the reference point. So this will be positive. So this is the reference point we are considering here. So VA1 with respect to the reference, it will be positive. Fine. And what will be VK1? So VK1 with respect to the reference point, it will be, see, the diode is not conducting, so obviously no current is passing in this circuit. So this terminal, this is a reference, and the K1 are basically at the same potential because there is no current flowing. So VK1 with respect to the reference 0 as reference O will be 0. So here VA1 is greater than VK1. So diode D1 will conduct. Fine. Now let's check for the second diode. For the second diode, what is VA2? Which VA2 basically means VA2 with respect to the reference. So we can see that the reference and VA2 are at the same potential, so it will be 0. What will be VK2? VK2 with respect to the reference will be, see, the K2 is now will be positive because we are considering the positive cycle, so this will be positive. So here VK2 is greater than VA2, means the cathode potential is higher than the anode potential, and so that too won't conduct. Okay. Similarly, let's check for diode 3. What is the voltage of the anode in diode 3? VA3. VA3 is nothing but VA3 with respect to the reference, and VA3 with respect to the reference, obviously both are at the same potential, so it will be 0 volt. And what is VK3? VK3 with respect to the reference, this is the VK3, and we can see this is connected at the negative terminal. Okay, so VK3 will be negative. So here VA3 is higher than VK3, so diode 3 will conduct. Okay, fine. And the last, let's check for diode 4. What is VA4? The VA4 with respect to the reference will be negative, and VK4, what is VK4? VK4 with respect to reference, since no current is flowing, we can see that the VK4 and the reference are the same potential, it will be 0. So here VK4, the cathode potential is greater than the anode potential in this case. So diode D4 won't conduct. Okay. So basically during the positive cycle D1 and D3 will conduct. Fine. So now how can I redraw the circuit? During the positive cycle the circuit will look like this one, because these two diodes won't conduct. So the current will flow like this. Okay. So what will be the voltage across the load now? V0. It will be same as that of the source. Okay. Now similarly check for what will be the waveform of the output voltage when there is negative cycle. So this is the negative cycle. So when there is a negative cycle, this will be the polarity. So now which diodes will conduct during the negative cycle? See, negative cycle means the positive will be like this, and what will be the expected direction of the current? It will be like this. You can see this current is trying to enter through the cathode of the D3. So when current tries to flow through the cathode, then the diode won't conduct. So this D3 won't conduct. Okay. So when the current tries to flow like this, obviously the current now tries to enter through the anode of the D4. So the D4 will conduct and it will allow the current to pass. Okay, fine. So now when this current, if the current tries to enter again the cathode terminal of D1, when the current enters to the cathode terminal, the diode won't allow it. So D1 will not conduct, and if this current tries to flow this direction, so here in for with respect to D2, the current tries to enter through the anode terminal, so it will allow. Okay, so this is the direction of the current. Okay, so here D2 and D4 conducts during negative cycle, and here D1 and D3 conducts during positive cycle. So how the output voltage will look like? during the negative cycle? See, during negative cycle, during positive cycle, how we have considered, this is the polarity we have assumed. During the positive cycle, current was entering this thing, the resistor in the positive cycle. If so, the voltage was like this. Okay, during the negative cycle also, the current is entering in the same way as during the positive cycle. See, this is the positive cycle, this is the negative cycle. See, the current is entering the positive terminal of the resistor in both positive and negative cycle, means the polarity of the voltage across the load resistance, that is here R, will be same for both the positive and the negative half cycle. So the negative half cycle also, the waveform will look like this. So now if you want to draw it together, both the positive and negative half cycle, suppose this is the input voltage, so the output voltage or the voltage across the load will look like within the positive cycle, obviously it's same as the input, and during negative cycle the voltage across the load is same as the voltage as it was during the positive cycle, because the current is entering in the same manner, in the same direction in both the positive and the negative half cycles. So the output voltage will look like this. Okay, this is the output of full wave rectifier. Obviously here also ripples are there. Okay, this is not a perfect DC. So again, so here also we can calculate the ripple factor. Ripple factor is V RMS by V average whole square minus 1 square. See, this average, V average, we can also denote it as VDC. So whenever you come across the term VDC, it basically means V average. Okay, so you can use either of the terms interchangeably. Okay. So what is the RMS value of this waveform, VRMS? So if you calculate the RMS value of this, what will we look at? It will be Vm by root 2. Fine. And what is the average value of this waveform? It will be twice Vm by pi. Okay. So what will be the ripple voltage? Ripple voltage will be Vm by root 2 divided by 2 Vm by pi whole square minus 1. So if you calculate, you will get the ripple voltage at 0.48 or 48%. So in half wave rectifier, what was the ripple voltage? It was 1.21, and in full wave rectifier the ripple voltage is 0.48. We can see that in full wave rectifier the ripple voltage is the ripple factor is considerably lower than the half wave rectifier. So the lower the ripple factor, the better is the outform. Okay. So the next thing was the conversion efficiency. So what is the conversion efficiency? The conversion efficiency is PDC by PSC. So it is basically the powered, both power is the power delivered to the load by the rectifier, and PTC is calculated with the help of average value I average square R, and PAC is calculated with the help of RMS value. Okay, fine. So again, this is the load we are considering is R load. So in R load, the current waveform, the shape of the current waveform, it's basically the shape, it follows the voltage waveform. So whatever will the voltage waveform, the same shape will be the current waveform also. Obviously the magnitude of the current will be different than the voltage, but the shape will remain same. Okay, so this was the shape of the output waveform of the voltage. So the input, the current will also take the same shape, but the magnitude will be different. Here the magnitude is Im, here the magnitude is Vm. Okay, again this RMS value of this waveform will be Im by root 2, and the average value will be Im by twice Im by pi. So what is the conversion efficiency? I average square twice Im by pi whole square by RMS square, Im by root 2 square. Okay, and if you calculate this, we will get the conversion efficiency like 81.2%. Okay, so it is a double than that obtained in half wave rectifier. Fine. So we can see that the full wave rectifier is much better than half wave rectifier in terms of both conversion efficiency and the ripple factor. Fine. And what was the conversion efficiency for half wave rectifier? It was approximately 40.6%. Rectifier is equal to 81.2%. Fine. See, this conversion efficiency we can represent as different forms. So this was the formula, and this was equal to the average square R by R, and here VRMS, IRMS, this also we can write. Fine. We can also write it as V average square by R. Here V is equal to I into R into IRMS. We can also even write that square by R VRMS into VRMS by R. Fine. So as per requirement, we can use whether to use the P is equal to I square R formula or P is equal to V square by R formula. Just remember, whenever we use this formula, this current, this I is the current that is flowing through this resistor. Okay, and whenever we use the terms V square by R, this voltage is the voltage across this resistor. Fine.